This is the second part of section 8.1, where we're going to talk about the mean and standard error for a sampling distribution. So in the first part of section 8.1, we talked about how to describe and define the sampling distribution, shape, center, and spread. We'll talk more about shape when we get down here to the central limit theorem, but we talked about how the shape might change. We looked at only a normal distribution to start with, but we'll see a skewed distribution in just a minute. And we also talked about how the mean and standard deviation of the sample could be very close to or different from the population standard deviation and mean. But now we're going to talk about what is the mean and standard error of the sampling distribution. So remember, that's the distribution of all the sample means that we've gathered. So we've taken lots of samples. We found the mean for all of them, and now we're going to turn that into a distribution. So what does that distribution look like? We're going to start with the example based on test scores for test 1 from this semester. And this is from all 3 classes, and it includes the bonus points that were added on if you took the test 1 addendum either in the testing center or online. And so you notice that we have some scores that are even above a 100. I think the max was a 105. And then of course we have skewed a bit down here because we ended up having, I think, 4 people maybe who did not take the test, and so that was 4 zeros. And we had a mean after the addition of points of 64 and a standard deviation of 24. That's very spread out. And this is a great illustration of a real-life example from where I took samples of size 4 from this distribution with the mean and standard deviation that was based on our class and the shape, this non-normal shape. And if we look at the mean and the standard deviation of this distribution, which we call the standard error, we notice that they're related to the population mean and the population standard deviation. And that's what we're going to really look at for this part of the video. Notice our mean is very close to the population mean. 63.7 is just a little bit below 64. And our standard deviation goes from 24 to 12. That's quite a bit of difference. Now notice the scale on this second graph is not the same as the scale above. But it's not as spread out. In fact, it's cut in half. 24 cut in half is 12. And it's not exactly 12, that's just been rounded. But there's our actual standard deviation at the bottom for all of our different summary statistics. But this is an exactly perfect description or example of what happens when we have a sampling distribution. All right, so in your notes, your guided notes from watching the interactive assignment for 8.1, you should have gone through and seen they should have talked about the mean and standard error for a sampling distribution. And so the mean of the sample means, so that's our notation, that's the mean of the sample means. So we use a mu for mean, and then we do a subscript of x bar just to identify it's not just the mean of the population. So mu is the mean of the population. Now this can get confusing to think that we have to have 2 separate notations because they are the same. In fact, we very specifically say that the mean of the sample means will equal the mean of the population. However, that notation is important. We want to make sure and keep the correct notation with the subscript to X bar. I know that doesn't look very small, but I write big with this stylus. But that's the mean of the sample means is equal to the mean of the population. When we talk about the standard error, or the standard deviation of the sample means, we just shorter to say standard error, then that is actually going to be different than our standard deviation of the population. And so hopefully you saw this, but the way we calculate our standard error is to do the standard deviation of the population divided by the square root of the sample size. So of course n is our sample size. And that will give us the mean and standard deviation, the center and the spread for our sampling distribution. So that gives us two of the three things that we need. So these two formulas are very important to know. Of course, the mean equaling the mean, that's not hard, but you need to know that that relationship exists. And then making sure that we divide that standard deviation by the square root of n, that's going to make our standard deviation smaller. So I think when you divide by a number, if I take the square root of a whole number, I'm going to get something bigger than 1. Of course, I don't have a sample of size 1, so I'm not going to divide by n equals 1. But n equals 2 or higher, any sample that I take, I'm going to have a whole number bigger than 1, so the square root is going to be bigger than 1. And anytime I divide a number by something bigger than 1, that number is going to get smaller. So that's what we're going to see as our relationship between the mean and the standard deviation of the population versus the mean and the standard error for the sampling distribution. All right, so the example with the test scores is interesting. It's got a somewhat skewed distribution, but it's also just 60 or 70 numbers. It's not a true whole population in the sense that we would normally be dealing with populations for statistics. So this is a distribution I can describe the population. I can say that, as far as shape, this is very left skewed or very skewed left without the hyphen. I can find the center. Luckily my computer program gave this to me, that the mean of the population is 81.4. And I can find the spread, and that was what the standard deviation is 10. So I can describe that population, and I'm going to take samples from this population. I'm actually going to take samples of various sizes so that we can see what changes as our sample size changes. All right, so our first example is with samples of size 2. And of course, this is just taking two things or people from the population, adding those two numbers together, dividing by 2, and getting the sample mean. And putting all of those sample means. So remember, each of these, the blue here is looking at lots and lots and lots of sample means. In fact, we've done 1,000 simulations of just taking 2 out at a time and finding the average. Randomly selecting 2, taking the average, putting them back in, taking 2 more, finding the average, putting them back in. And as you can see, it's kind of hard. It's only probably 1, but there is a sample mean way out here to the left side. And so the black curve that's already on the graph, that's what the normal curve would be. What I'm going to draw is going to be what I assume is kind of like the actual shape. That wasn't very smooth, but you get the picture. And our sampling distribution is still skewed left. Maybe not as skewed as our population, but there is still a skew here. Now, what's really interesting, however, so the shape, we don't know much about the shape yet. In fact, that'll come when we talk about central limit theorem. But my mean of my sample means should be 81.4. And in fact, if we round to 1 decimal place, it is. The standard deviation of my sample means should be 10 divided by the square root of 2. And when I calculate 10 divided by the square root of 2, I get 7.07. So this is, I guess, the theoretical values. Based on the mean and the standard deviation, I can find the mean of the sample means and the standard error. Now, my standard deviation isn't right on, but it's pretty close. 7.2 and 7.1, if I were to round both of those to 1 decimal place, are fairly close together there. So it's not far enough off for us to think that something wrong happened. So our mean and our standard deviation still hold. Here's an example with a sample of size 4. So these are 1,000 samples of size 4. And this is still got, so again, the black curve represents the normal distribution. This one is still kind of skewed a bit, but not as much. Notice there's not anything below, 60 or maybe even 65 where that very lowest number is. And again, our mean is spot on, slightly different, but very, very close. And we should have had a mean of 81.4. We had 81.42. And we should have had a standard deviation, or standard error, excuse me, of 10 divided by the square root of 4. Of course, the square root of 4 is 2. 5 divided by 2, or excuse me, I just said the answer. 10 divided by 2 is 5. And we were at 5.1. So again, we're super close to what we expect. So even with small sample sizes, our mean and standard deviation are going to follow these formulas. All right, so take a second and find out what should the mean and standard error be for a sample of size 16. And pause the video and go ahead and calculate those, and then go ahead and hit play again, and I'll go through those. Okay, so hopefully you actually did pause the video and calculate. Of course, our mean of the sample means should be the same as the mean of the population. So we would expect 81.4 again. And our standard error will be the standard deviation divided by the square root of 16. So that's going to be 10 divided by 4, and that should be around 2.5. So those are the values that we expect to see. Let's see if that's actually what happens. And sure enough, here we go. Here's our sampling distribution. This is, again, 1,000 simulations, but now we've had samples of size 16. Notice the blue still isn't perfectly within that black line that represents our normal curve, but it's much, much closer. It's definitely starting to normalize or take on the shape of a normal distribution. So what we expected from the previous slide was to have a mean of 81.4. I was just slightly higher at 81.47, but again, it's still super close to what we expect. And our standard deviation, this is the closest yet that we've gotten, 2.51. So we're 1/100th off. So 1 over 100, that's 0.01. That's very, very close to what we expected our standard deviation to be. All right, so once again, see if you can calculate these one more time. What will the mean of the sample means and the standard error for the sampling distribution be if we take samples of size 36? So go ahead and pause the video if you'd like, calculate these, and then I will go over them when you come back. Okay, welcome back, hopefully, or I'm just, acting like you did. I'm assuming that you paused and calculated. So here we've got a mean of our sample means. Should be, of course, 81.4. Remember, that's just going to be the mean of the population. It's going to be the same. We expect the center to stay put. We don't expect big shifts of where the center of these distributions go. The standard deviation, however, of the sampling distribution, or the standard error, now we're going to expect it to be 10 divided by the square root of 36. So, of course, that's 10 over 6, which will be 1.6 repeating. To be honest, a lot of times when I'm working these problems out, I'm writing things down because our calculators will allow us to type them in like this. I actually just leave the standard deviation written this way, just 10 divided by square root of 36. Even though I know that the square root of 36 is 6, or the square root of 16 is 4, the square root of 4 is 2, it doesn't matter. We're going to be able to type it in our calculator as a number divided by the square root of a number. And we don't have to try to put the estimated decimal in. So I usually just leave it like that. The reason I'm calculating in these examples is simply so we can compare the decimal values to the graphs that we get, the actual samples and simulations that we're running. All right, so before we look at the sampling distribution, I just wanted to show one more time. So, of course, this is our population distribution on top. This is what we started with at the very beginning. It's just our very left skewed distribution with a mean of 81.4 and a standard deviation of 10. Here is one sample, a single sample of 36 that was taken. And notice that the sample is still very skewed. It almost, other than the fact that it's a histogram rather than a smooth curve, it really does seem to follow the same shape as our population. Our mean is a little bit different. Notice it's higher, 84.1. Standard deviation is slightly smaller, 8.21. But that sample mean, that 84.1, that's going to be one value in our sampling distribution. So we're taking all of those sample means. I know I keep repeating it, but we take all of those sample means and we turn that into a new distribution. So let's see what that looks like. And sure enough, once again, here we have the values we expected. The mean of the sample means to be 81.4. It was 81.43. And the standard deviation of the sample means, or the standard error, we expected to be 1.6 repeating. And I believe this just rounds to 2 decimal places. So 1.67 would be 1.6 repeating rounded to 2 decimal places. So this is very, very much what we were expecting as far as our mean and our standard deviation. But what I would really like to point out, and this is our next point that we'll talk about in part 3, is what's happening to this shape as our sample sizes increase. That's the very interesting part, and that's what our central limit theorem will tell us.